name is John Tressel, and I'm proud to say that I'm the 2026 ARCS Scholar for the University of California, Santa Cruz Chemistry and Biochemistry Department. My thesis research has been on materials catalysis and electrocatalysis. So let's go take a look at that today. What is holding back improved hydrogen peroxide production is a lack of effective two-electron reduction reaction catalysts. The main issue here is the selectivity versus the four-electron reaction, which produces water. This can be overcome by active site design, specifically with a metal N4 active site, which allows for the end-on binding of O2 gas, which favors the two-electron pathway, versus a metal cluster active site, which favors the four-electron pathway. However, production of metal N4 sites in conductive materials has previously been rather difficult due to the thermal instability of the metal-nitrogen bonds. If these limitations could be overcome, the industrial production of hydrogen peroxide could be improved as well as used for the simple disinfection of water sources for drinking water or agriculture. To get around this, in the Xiaowei Chen lab, we've been utilizing a new fast synthetic method known as magnetic induction heating. In the video near the right, you can see a metal reduction process that typically takes several hours completed in only 10 seconds, when that white powder turns into a black powder. This is done by utilizing strong magnetic currents to heat up an iron sheet to over 1,000 degrees Celsius in under 10 seconds. This rapid heating and cooling can be used to generate metastable materials, and we used it along with copper chlorophyllin to produce a graphitic material which is highly conductive with copper N4 active sites, effective for the two-electron oxygen reduction reaction. To determine the electrocatalytic capabilities of the material, we used a rotating ring disc electrode to conduct linear sweep voltammetry. This allows us to vary the electrical potential at the disc electrode to determine the energy needed to generate products and to determine the selectivity of those products at the ring electrode. With this, our sample is able to reach nearly 90% pure hydrogen peroxide with a very minimal overpotential of about 20 millivolts and acidic, neutral, and alkaline electrolytes. To prove the direct water disinfection capabilities, we produced a neutral saltwater electrolyte that we spiked with E. coli, a common gram-negative bacteria found in the human gut and sewage. When we applied a current to our electrode setup, we were able to see significant bacterial inhibition after just 20 minutes and complete inhibition of bacterial growth after 40 minutes. This showcased how our sample could be used for both industrial production of hydrogen peroxide as well as on-site water disinfection for agriculture or drinking water. And with that, I'd like to thank ARCS for their support, all of you for watching my little talk right there, and I hope all of you have a great symposium for ARCS 2026. Bye.